Yeah, I think, yeah, it's recorded. Okay. Fine. So yeah, welcome to the I guess the 10th lecture of this course on generative modeling, and we have gone far from VAs already. So we looked at VAs, and we looked at GANs a bit, and last class we discussed about diffusion models. So we gave some intuition about from physics what diffusion process is, and how that could be used in our usual in our thought process of modeling a data distribution. So two things very similar to diffusion process. One is something called as the forward process. So where we are going from the data, which is mentioned here with x0, to something called as x infinity, which is pure noise, right? And we do that by adding very small amounts of noise at each step, right? So what ends up happening is any kind of correlation that exists in the data that makes the data is lost, right? So at the end we have only pure noise left as the byproduct. And the way we look at it is basically we add something like a Gaussian noise, again scaled with some factor, and the factor is between 0 and 1, right? And we again saw about how this could what could this mean in terms of getting so because it's a process with the forward process, so it doesn't we also came to a formulation where we don't need to go through all the steps to arrive at a at the noisier version of the same image at a given point t, right? We said we can just look at that as a Gaussian distribution in itself, right? Which makes it easy to get any xt from a given x naught, right? For any t, uh, instead of going through the whole process from 0 to t, right? And then we made a claim that okay, if this is the forward process, can we learn the reverse process, right? And where we used a result of some previous this one result that's saying that if the noise added are actually small, then we could then we the reverse process has the same identical same functional form as a forward process. We use that to intuit something about the reverse process which are naming it as p theta, right? Something which we want to learn. And we then spoke about this idea that okay, now that I have this p theta, this could I would model this would be my model distribution. I need to minimize the KL between them, which is same as maximizing the expected log likelihood, right? And we then use the variational argument, same like in VAs, which is why it makes sense to talk about these in VA lectures, because they are sort of like a extension of VAs, where we looked at all of these noisier version of the same image as the as a joint conditional distribution. And we then came to a solution, after a lot of math, to into this idea that I could write, or I could get the log likelihood by sampling from this particular distribution. So we had something which looked like the first term of the VAs, where we try to reconstruct the image from the latents, but here we're using only the first noisy version of the image, versus there is some KL term between two Gaussians, right? And we said that this sort of an expectation, because we cannot compute in closed form, we would need to sample the values. Now, because we are sampling two random variables, very clearly it will have some sort of I mean, more variance estimate compared to a single random variable sampling, right? And we also had a doubt regarding this point, right? So where we said that okay, is xt plus 1 and xt minus 1 conditionally independent on x naught, and that is true, because we can always write something like this, right? We could write this as this is the conditional distribution of the joint of t plus 1 and t minus 1. This can be seen as conditioned on xt minus 1, right? This is again from the simple conditional probability formula. Now the point is, this distribution is same as this because of the fact that if I tell you what x naught is, I can get the complete distribution of xt plus 1. right? So knowing xt minus 1 doesn't give me any extra information or doesn't influence the xt plus 1 distribution in any way, right? So therefore, given x naught, xt plus 1 and xt minus 1 are conditionally independent. And that basically boils down to this, which is exactly what we capture in this idea of conditional independence, right? So hopefully this is clear. All right, so this is true. Now, then we said, okay, we use some math jugglery to see if we can bring down the variance, if we can bring down to sampling just one random variable instead of two, right? And we used two ideas. One is the Markov assumption of this forward process and the Bayes theorem to, see, to basically rewrite this whole expression in terms of this distribution, that is q of xt minus 1 given xt given comma x naught, right? And we did again some sort of math jugglery and we came down to some expectation of again the KL divergence, but we don't know whether this was Gaussian or not, and that is exactly what we left in the last class. So basically the idea being that because this xt minus 1 given xt comma x naught can be seen as the ratio of two Gaussians, and intuitively speaking, because Gaussians are basically just exponential, proportional to some exponential terms. So hopefully, if I were to look at multiplication of two exponentials and divide by two exponentials, if we could get something of the Gaussian form, then the evaluation of the scale divergence will be very simple, right? So we left there, and turns out to be it is true. So if you can, I've never worked out the math yet, but you can substitute the Gaussian distribution formulas here. And what will end up happening is you will get this q of xt minus 1 xt comma x naught as a Gaussian distribution over xt minus 1 and having the parameters xt and x naught, right, in the mean, and the variance being the variance covariance matrix being just a term which depends only on time, right? Which is again sort of obvious because the whole process that we were considering was also just the variance was depending only on time. Only the mean was changing with respect to the the condition variable, right? So this I will term it as sigma, capital sigma q of t, right? Q for the forward process, and this is the variance covariance matrix. And very simply, this can be seen as some diagonal matrix, some constant into times I. Now, one point to remember is that this value is always positive, right? And because it is positive, this matrix sigma q is invertible, and because invertible, this distribution is non-degenerate, right? So it is not degenerate. So basically, it's a valid distribution, and that value is captured in this sigma q square of t, right? And this mean
degenerate means what? Sorry.
Yeah, so degenerate is basically where when you have a Gaussian distribution, it's possible that the variance covariance matrix it turns out to be not um, uh, invertible, right? Because in general, variance covariance matrix, for example, for any random vector, is actually just PSD. It's symmetric and PSD. Right. So if it's possible that one of the eigenvalues turns out to be 0, and if that happens, sigma inverse won't exist, right? So this basically, so basically, what will happen is you will have like it'll be like something like a sharp curve like this, like a delta function, thing. At some point, basically at mean. Correct. It come out to be like this, right? This is basically same like saying if I have a single random, single Gaussian random variable, right? Let's say mu and sigma. If this sigma was set to 0, right? Yeah. So if that happens, then you will just have like a straight line like this, right? At the mean parameter, and this will be infinity. It will go up to infinity, right? So same like that, basically. So because it's always positive, right? Because alpha t is always less than 1, and therefore all of these numbers are positive, and therefore this whole thing is positive. So we don't need to worry about that part as such. All right. Okay, and we have this complex looking expression for the mean of this distribution. So now very simply we'll use this idea of K between two Gaussians to come up with some closed form solutions. Before that, this is what the final expression looks like. So you have the this is sort of like the decoder term of VAE. Again, to recall, right? We're going from latent to data, and this is the additional part of the this one. So where in VA we just had one KL term, here it is summation of expectations of KLs, right? There we didn't have any summation, we didn't have any expectation, nothing. It was just one KL term. Here we have multiple such KL terms with an expectation and with some summations between them. All right. Okay. So now we'll close this formulation problem and hopefully go into implementation, how we want to implement and stuff like that. Okay, so just to recall, this is the form we just saw just now, and this is the Q of xt minus 1, right, with some mean and some variance, which is defined like this, and p theta of xt minus 1 given xt is also a Gaussian distribution from the assumption that we had. So if you remember, we did the KL between two two Gaussian distributions, right? So that we'll use that here. Yeah. So this is the KL between two Gaussians. So what we'll do now is we'll see that. Sorry. Yeah. So. So what the first thing that we will do is basically look at something like this, right? So so the authors, what they do is, see, you want to make these two distributions as same as possible. Now both are Gaussians, so basically we want to make the means very similar and variance is very similar, right? So the first assumption what they do is they take this sigma theta of xt, right? That is the variance of this particular term to be equal to sigma q of t, right? This is they say to make sure that the KL divergences match more, right? The other approach, I mean the VAE approach was not this, right? In VAE we were also trying to estimate the variances also, right? We were so from the encoder we used to get two sets of vectors. One was the mean vector, one was the variance of individual components vector, and we should use that to sample a value from the distribution, right? So this is one leap that they take, one sort of assumption, and the other assumption is basically, and this is something that it's actually my fault. So let me go back here in the forward reverse process formulation. I said that this is mu of xt comma t. Now, while that is not wrong, but one wouldn't expect this to come out to be like this always. So let's call it, let's frame it properly. So this is what you would want. I mean, this is what you would say, right? Some mean on xt, some variance on xt, right? Now, so the formulation that the authors do is basically saying that I will not learn different mean functions for different time points. Rather, I will have the same function, but I will pass the time parameter into it, right? So basically, we are saying that whatever changes between xt minus 1 can be captured using this time variable alone, right? This is the second assumption that we are taking. Now we are free to obviously have different mean functions for different time points, but this turns out to be a better approach because of the fact that you share a lot of variables and the learning becomes simpler. That's the idea. Is that clear?
Yes, that's clear.
Okay.
So
yeah.
Okay. So in variance, we are just assuming that the variance is like not dependent on. So variance is still on dependent on time, no?
Correct. Yeah. So variance is dependent on time. It doesn't depend on xt. That's the assumption.
Right. Mm-hmm.
Yeah, because see, when you model it like this, there is no reason why you should assume that it doesn't depend on xt and why it should depend on t and all of that, right? At the end, it is some function of xt, right?
Correct.
We have access to a small t also as part of this reverse process and forward process. We'll always know at which time point we are in, because that's how we will, simulate the reverse process or forward process.
Right.
So we have access to that, not a problem. But the point is that it's not immediately apparent.
Basically, a function of data.
Yes, of the data. So here what they're saying is, okay, we will not do that. Rather, we'll assume it to be same as the reverse process for a variance. Yeah.
Yeah. Fine.
Okay. And see here one more thing you need to see here. See this reverse process. So this is also actually some sort of a reversing of the forward process, actually speaking, right? But this movement from xt to xt minus 1 is conditioned on x naught.
Right.
It's very important. So conditioned on x naught, then when you look at this, the variance of this random variable in such system, that turns out to be something which doesn't depend on the data at all. It just depends on time. Right? Whereas here we haven't made that assumption at all. We never look at conditioned on x naught. We're just looking at xt to xt minus 1. Right? This is also a leap in that sense, actually. Right? Hello? Hello?
I'm back now.
Oh, okay.
Yeah.
Yes. So I was saying that this is basically reversing of the forward process in some sense, but conditioned on x naught, right? This is not conditioned on x naught at all, right? So this leap is also in some sense a bigger assumption in that sense also, right? Yeah.
Right.
So yeah, this is also something that we need to keep in mind. So now it's very simple. Just plug and play this, KL divergence. So we'll just, so basically now the point is, we wanted what? Oh yeah, Q and P. Yeah. So again, this is just a general this one. So if you see here, this will turn out to be half of. So the KL divergence we are trying to see now. So KL between the Q distribution of hours, that is Q of xt minus 1 given xt comma x naught with P of theta of xt minus 1 given xt, right? This turns out to be basically half of log of, again the variances are same, so this will just turn out to be log 1. I'll not do that. So half of log 1, right, because same variances, minus d by 2 plus half trace of sigma q inverse sigma p. So here sigma q, the q is the second distribution. So this inverse of this is the same matrix again. So it just turn out to be a I matrix plus half of mu q, right? This distribution minus mu theta transpose and sigma q inverse, that is this inverse, that is again same sigma q inverse here of t, and then same thing mu q minus mu theta, right? And then what will turn out to be, so this all goes out to 0. Trace of I is d by 2 minus d by 2 is 0, and this turns out to be half of sigma q is basically sigma q squared of t into I. So 1 by, so inverse is going to be 1 by this. So 1 by sigma q square of t into I, and this is then your vector transpose vector is basically the norm, right? L2 norm squared. So this mu q minus mu theta minus mu theta square. Right? So turns out to be, so this is the KL divergence. Now, how will we look at the, so what will basically happen? You will just have, mu q minus mu theta here. And so if you see here, this basically turns out to be a very simple MSE sort of a formulation, right?
Yes.
Right. So we are trying to match the mu q vector with mu theta vector, right? Each pixel by pixel, right? I mean, if you're talking about images, pixel by pixel, right? So each component by component. This basically turns out to be some sort of a MSE formulation, or in some sense regression, right? So this is something that's very interesting, right? Because all of that computation, everything came down to simple sort of a formula problem, and that is all. Again, it came down to it because of a lot of assumptions, but practicality shows us these assumptions work. So we can go ahead and do this sort of thing. Now this is fine. This is one way of solving the problem. The authors look at this in one more way. So we know what mu q of xt comma x naught is, right? That is this formulation. Now what they do is they rewrite this mu theta of xt comma t in this form, right? So where we are saying that look, mu theta of xt comma t, because I have access to xt, right? So what I will do is I will, whatever the learnable part is there in mu theta, I will write it as xt in this form, x theta of learnable part, and to get the mean, I will now do all of this jugglery, right? I'll multiply, add, whatever, right? This is the point. Now, if I do it in this way, what does the problems move down to? If you see here, I'm sorry, go ahead.
Please repeat this part, second part.
Just a moment. Just a moment.
Sure, sure.
Yeah, some noise, background noise. Okay. So the idea is, yeah. So the idea is, see, mu theta is some learnable function, right?
Yes.
So now what we're doing is we're saying whatever the learnable part is. So because see, it's a learnable function, so I will parameterize the learnable function in this way, such that all the learnable part should be in this
Okay.
Yeah.
Okay.
So yeah, so I'm saying this learnable function, I will write it in a form of one another learnable function. That's it. Right now, why is that interesting? Is because and see, we have all of these variables available with us. Xt is known because this learnable function will also had access to xt, and t is also known. So I know all of these alphas and whatever, right? So now, if you look at if I were to look at this mu q minus mu theta squared, it will turn out to be with some factor which depends on t into this x naught minus x theta of xt comma t. Is it correct? Right? Because these two terms will get cancelled. Let me just, yeah. So this is exactly the same as this term, right?
So first term gets cancelled out.
Sorry?
So first term is getting cancelled out, and
first out. And whatever remains is something that depends on d alpha, is some variations. And finally, what depends is x naught and x theta comma x theta of xt comma t, right? Now, just see how we're trying to interpret this. The point. So what are we saying? We're saying you have to match. So the network x theta will be given the noisy version of the image, right?
Right.
And the time at which the noise was added, let's say,
right,
which noisiest version, and match it to the actual image.
Yeah.
Correct. Right. So it's basically telling you, okay, I had x naught, I moved to xt after a fixed t amount of time. I'll give you this. I'll give you at what time point you are. You have to give me x naught. Right. So this brings this diffusion model into a bit more sort of intuitive footing in that sense. Right. Okay. Clear until now?
This clear.
Okay. Now we'll look at one more parameterization. So let's say I know how xt I can get from x naught, right? Xt is basically some Gaussian distribution we discussed, right? because Q of xt given x naught is some Gaussian, right? And that Gaussian is basically, if I write it in this format, where epsilon naught is basically some Gaussian noise, I get in this form, right? So xt is basically x naught plus some noise. Now, scale noise. This means I can write x naught as xt minus the noise divided by this factor root alpha t bar. So I'll put this x naught, okay, in the mu q equation. So mu q we had here, right? So let me get that here again. Oh. So I can now get this mu q and put the x naught value in this mu q expression, right? And what will turn out to be is it will turn out the mu q will turn out to be something like this, right? Put x naught here. Okay, so I will get this form. Now what I will do is I'll reparameterize the mu theta in a different way now. That is basically saying, okay, whatever 1 by alpha t xt minus this, with this is the learnable part now. So all the learnable part has to go here, and all of this gets added up to get the actual mean, right? So now again same thought process. We look at mu q minus mu theta, right, squared. This turns out to be basically some factor. Again, these two will get cancelled, right? And what will end up happening is we'll get this into these some factors into this part, epsilon naught minus epsilon theta of xt comma t. So do you want to try to interpret this?
Yeah, sure, I'll try.
Yeah.
So epsilon naught was the original covariance matrix of the data. Is that correct?
No. See, epsilon naught is this, right?
Oh,
To
okay.
go from x naught to xt, this was used as the Gaussian,
Yeah,
transform.
correct. Yeah.
Hmm.
Okay, now we can go ahead. So epsilon naught is like the normal distribution. Okay, so are we learning the parameters? So epsilon theta we are trying to learn. Are we trying to learn the set of parameters such that it makes the data like normal distribution, such that it makes the makes it zero mean and like unit variance?
No. So what has to be what has to become zero mean unit variance? The data, is it?
Not the data, but like the output of this epsilon theta xt comma t.
Right. Yes.
Right.
But there is some subtlety still involved in that.
So basically, we are trying to learn the parameter. So basically, it's a transforming the data.
Okay.
So learning the parameters so that if you give input as xt comma t, the output is a normal. I don't know how to put it. Output is output we know. Output should be like normal 0 1 0 I.
Okay. So you're saying epsilon naught of epsilon theta of xt comma t should basically output a Gaussian distribution. Is that right?
Yes, that is what I am saying.
But so that is trivial, right? What I can do is I can just
Widening
say.
transform.
Correct. No. So what I can do is I can just ignore xt everything, right? I can just have this function epsilon theta, right? Theta parameters. There's nothing to learn. You just output Gaussian distributions always.
Okay.
There is some subtlety involved in this. You'll need to look at xt for that.
I want to transform this xt into some way so that it the output distribution follows a normal distribution.
Yes, but we're still not discussing. So okay, so more than thinking about it being a normal distribution, think of it as think of it as this is the cleanest data. This is some noisy data.
Okay, fine.
Right. So we added some noise to this data.
Right.
Data to get the noisy version.
Correct.
Right. So then what should epsilon theta do to match? So basically epsilon theta should predict what? The noise, right?
Okay. So epsilon theta should predict noise that was added to xt so that it become like a normal distribution. Such that it became a norm. Okay. Fine.
Correct. So basically, see here, this xt has some. So I was saying some subtlety in this, right? Basically, epsilon theta takes your xt, but this xt was generated with epsilon naught.
Right.
So let's say some, I mean, whatever the function that we had right previously. So this is basically x naught plus that epsilon naught. Again, some factors, just bear with me, right? So we added this noise epsilon naught to the data to get xt. This is xt, correct? Yes. Now, so what we're saying is I will give you the noisy version. I'll give you the t, predict what was the noise that I added.
Right.
Yeah, to get the noisy version.
Right.
So that's how we relate the epsilon naught here and what epsilon theta should predict. Because if you were to just say that this should match a Gaussian distribution, that is not right. It was the noise that was added to the x naught to give me xt. Right. That is the relation with. So this is basically then it becomes more similar to the idea that there is some target and there is some prediction to be made. Right. So this is the true noise. This is the prediction of the noise, and this needs to be similar. That's the idea. Yeah.
Right.
Okay. So now let's look at the final
denoising operation on xt.
Exactly. Yes. We're trying to learn a denoising transformation. Exactly what we're doing here also. Right. So I mean, yeah. So here the idea was you give me the image directly, the denoised image. Yes. Here we're saying give me the noise that was added. Image with the noise. Yeah. Right. Okay. Now again, so let's go back to this my main formula, main equation. Here the idea, so here the idea is that we want to maximize this lower bound, right? Which means minimizing this term, right? We want to minimize this term, right? Now the other point is that we also want to maximize this term. Now this term we already know how to maximize, right? You will just have a decoder which takes in x1 and spits out the real image, and you will try to solve this using, let's say, some Gaussian assumption or whatever, right? That's the usual way of solving things. So we'll ignore this for a while and we'll come back to it after we discuss this humongous part of the equation, right? So basically what we want to do, we want to minimize this part, and we saw three different ways of getting the KL term, right? So in the first way we had so this turns out to be something like this, right? Some function that depends on t, some scaling factor with this mu theta and mu q of x naught. Yes. Okay. So one thing what the authors do regularly in the paper is that they ignore this this part, the the scaling function, and they treat all of this to be equivalent in the sense you don't scale it with time. So rather this becomes basically something like this, right? Q of xt given x naught, something like this, mu theta of xt comma t minus mu q of xt comma x naught.
Okay.
Now, how would we operationalize it, by the way? So now we want to operationalize, we want to go to implementation. So how would we do it? Simple. Go ahead.
Operationalize meaning learning the parameters.
So okay. So yeah. So we have an expectation here, right? So can we compute the expectation?
I see. Okay. Yes. So because we have a complete expression of because xt given x naught and q, we have a definite expression, so that we know. And mu q xt given x naught also we know. Mu theta xt given t we don't know. We don't know, but we have a neural network which has some parameters, so we can like estimate it. So yes, we can do it like that.
Right, Hannah.
Yeah.
So okay. So how would we compute the expectation then?
By the usual formula which we use.
So will we get a closed form solution for this expectation?
No, we will not get closed form solution.
See, at the end, what we want to do, we want to learn the neural network parameters, right?
Parameters,
so,
yes.
And be able to compute gradients. Okay.
Right.
Now, I have a function which depends on the parameters, right? So I need to be able to compute gradients on this, but I have this expectation sitting here, right? Yes. So how do I go about, implementing this? So sample estimates, right?
Sample estimates, yeah, correct.
Right, sample estimates, right? So we'll do something this. We'll say, okay, I will draw, let's say, some n samples or whatever, right?
Yes.
Of what samples of what we will draw? xt, right? From which distribution?
Which distribution? xt given x naught. So
right, given x naught.
We already have the expression for that, so we can sample.
Right, that's it, right? So this basically we know xt is some scale version, all of that, right? Yeah. Something like this. But the point being that I can now sample these multiple epsilon naughts, right? Get multiple x naughts for a given multiple xt's for a given x naught. That's it. Yes. Right. So get, let's say, 1 by n. Let's say I equal to 1 to capital N, right? This will become mu theta of xt ith sample minus mu q of same xti comma x naught, right? And where xti is. Yeah. Go ahead.
So x naught is here one particular image, for example, not the entire distribution of images.
No, correct. Precisely. Yes. Because all of this what we have done till now is for one x naught. So if you remember the way we started is again same like in VAs, right? We first derived a point of a likelihood estimate for one value. Right. And then we complete everything saying, okay, oh, now we'll look at expectation over all possible, right? That's the idea. That's it. So this becomes xti. This becomes epsilon naught I. Epsilon naught I is sampled uniformly from Gaussian distribution. Simple and straightforward, right?
Yes.
Okay. Now, this is the first way of looking at things. Now, second way is similar, but so third way, how will we do this now? How will we operationalize this particular sort of expression? Let's say here you were doing mean to mean comparison, right? Yes, how would we do this here?
So you want to compute the expectation.
Give me something like this, something which I can write, which I can implement, right, at the end of the day.
I see.
So again, ignore this factor.
Yeah, I'll ignore it. Yeah. So this is also similar, like I don't think any.
Okay. So yes.
Summation of t equals to 2 to t, capital T.
Right.
And again, like some sample is okay. So maybe like given that we want to find the noise term here, we may need to sample multiple times and then compute one noise term and use it in this expression.
Okay, in the sense?
In the sense, just show me the previous expression once. Yeah, this is enough. Yeah. You are taking n samples. So, okay, got it. So, summation I equals to 1 to n.
Okay.
To n, and this will be like so exactly the same procedure. So I think so. So
okay.
epsilon like so norm of epsilon theta xti comma t minus epsilon naught.
Epsilon naught or epsilon naught I?
Okay. So I'm thinking about it. No, epsilon or not only.
Acha. So I think the authors are wrong then.
Okay.
so think about it.
Ith sample, yeah. Ith sample from that normal distribution, yeah. So yeah.
Right, Anna, because exactly what you said. XTI.
Because
what noise was added to get this XT from X naught?
Yes.
Anna, so where, as you said, the same thing. XTI. This repeats here. This can be repeated here. Yeah. So the noise that was added for getting the ith sample, you take that and you give that here, and yeah, again, it's fine, right? This is right. Okay. Now there is one other thing that the authors do, a bit iffy, but this is important for implementation. Okay, so I'll take one small detour and I'll write it here. So I had this, right? I had 2 to t q of xt x naught. And by the way, this is not the right way of writing it, but let me just make it a bit more clear. So expectation of epsilon naughts, right? Because that's the random variable. And yeah, epsilon theta x naught and epsilon naught, you take some function and t. That's it. Okay, so this is epsilon naught minus. Okay, so so if I ignore this scaling factor, this is what it turns out to be, right?
Correct.
Okay, now what we can do is I can look this summation as an expectation,
right?
Where t is sampled from u of t to 2 to capital T.
Correct.
This same expectation copies down, right?
Right.
Into 1 by t minus 2, I guess, because right, to make sure it's distribution. But again, as we know, this doesn't depend on the parameters theta. So whatever means it's just a scaling factor. So people just go ahead and ignore it, right? So no problem, right? So now the point is, what they do is they don't run this thing for all the time points. Rather, even the t is sampled.
Okay.
from T2 to T, right? So you take, let's say you define number of samples from this uniform distribution. So then you say, okay, this is now approximated as T going from some, so 1 by or whatever, right? Some fixed number of from this set 2 to T.
Right. Some randomly sampled. Yeah.
Randomly sampled numbers. And then you run this expectation. We already know how to do estimate, right? That is then now plugged in here, right? Now this was basically done because of the fact that running from 2 to capital T, it's a very expensive process. For every and this needs to happen for every X naught in the batch, and then T generally goes to thousands and all, right? So this becomes very computationally challenging. This one, what they do is they just sample some in the initial part itself, and then they run the values for those samples.
And what is the typical value of n in these cases?
Which n? This n?
This n, yeah.
Oh, actually, I'm not sure. I'll have to check.
Okay, that's fine.
Yeah, I'm not sure what.
But must be like maybe hundreds.
Yeah,
yeah. Few. Okay.
But no. But the thing is, see, you could even again the expectation at the end of the day. I can take whatever capital N I want. I think they'll just take one n. N is equal to 1.
Okay, fine.
See, because the thing is, see, this is for one sample, so they need to run this for how many ever samples in the batch. So then, so the hope is that over time, every image will get, will become a part of the batch, right? And it'll get sampled at least once. Hopefully, over the course of multiple epochs, this expectation will start converging to its this sample estimate will start converging to its true expectation.
Right.
That's the thought process. Right. Okay. So now we are almost there. We know how to compute the likelihood function and everything. So how would we go about implementation? So give me what all things would we need to implement this let's say this particular formulation. Let me get this also, for example. Yeah, I'll get this. So let's say, oh, not this one. Yeah, this one. So authors again they say that they got good results when they use this noise formulation sort of a thing instead of the mean formulation and all of that. I guess they're all empirical questions, no justification there. But yeah. Okay, so how would we build the network? What will be the output? What will be the input? What else is required? To make sure that we have an end-to-end solution to solve, right? That's the question.
For this particular term.
Yeah. For this particular term. Let's
So input would be d-dimensional.
Right.
So input dimension would be d.
Okay. So a d-dimensional vector goes here. What else? So what all will the network have to take as inputs according to this formulation?
Take as what?
Inputs.
Oh, okay. T also, time.
T also, right? So T also some number between 2 to capital T.
Right.
This goes as input, right?
What's the output? So D plus 1 dimensional input.
Correct.
Now output should be right.
So one thing is very clear that the output has to match the dimension of epsilon naught.
Yeah.
What is the dimension of epsilon naught? So we have been talking about epsilon naught a lot.
A D-dimensional only?
Correct. That's it. Right. Because what are we doing, right? What did we say? We said xt plus 1, at least in the form of formulation, is some xt plus some noise, right? This exactly the same noise. Now this noise is really the same dimension as
same
xt.
dimensions. Yeah.
That's how. That's it. This is the input output. That's it. Nothing else. Now this, so generally they implement it like this. There's something called as unit architecture.
Okay.
It goes to a lower dimension and tries to come back, that whatever. And also another issue here is generally the network. So they tried, giving this T as a single variable, just one number basically into this input. Turns out that the network starts to ignore this T for whatever reason. Because it's just one variable that's coming in, right? So, and this is our d-dimensional thing. So what they usually do is they implement this using something called as time embed, sinusoidal embeddings. So the basic idea I will just inform sinusoidal embeddings. So the idea is this T is used to form a vector which is of some frequency 2 pi ft, sine of 2 pi ft and cos of 2 pi ft. Okay, so this T is encoded like this, right? And for multiple different f's, right? How many different f's? D by 2 number of f's. Okay. So what you do is you will get now a total of d-dimensional,
d-dimensional time input.
Correct, d-dimensional time input, right? So then that is then added to the xt.
Right.
So xt plus this d-dimensional time embedding is passed as the input to this network, and then it's supposed to give the noise. That's the idea.
Right.
Okay.
So just some hack to make time dimension important, so that network starts caring about it.
Network starts caring about it. That's the point. Yes. Okay. This is the implementation part of it. One part of it. There are multiple different parts in this whole formulation, if you remember, right? So there is this alpha t's.
Yes.
Right. Again, we're ignoring for now in the loss function and all, but ideally we do need something like a alpha t schedule. It's called, right? Something which tells you at each time, at each t, what is the corresponding alpha t, right? And generally they use something called as cosine schedule. So something like for t equal to 0, it's a high value, again below 1 and above 0, and then it drops off like a cosine term, right? So between 0 and how cosine behaves between 0 and I think pi by 2, right? They try to simulate this using these are the values that alpha t finally gets over capital T number of time points.
Okay.
So this is the other part of the puzzle, the scheduling part, and then the only part remaining is the first term that we talked about, right? The decoder term. Right. Now this decoder term is generally not implemented at all. Rather, what's done is during the sampling process, they just so because at the end what you will get is you will get x1, right? All of that we did till now, if you look at it, right, it's about going from xt to xt minus 1, right? And this t is to capital T. So what you can do, the maximum you can do is you can go from x2 to x1. Now, then what they do, they just ignore the decoder term altogether and continue the sampling process to go from x1 to x0. That's it.
Okay, okay.
Yeah, so there's no separate, network learned, because ideally now that's the same thing what happens in the VAs, right? VAs, we have this is a separate network in its own self called the decoder,
Yes.
right?
Mm-hmm.
And this part, merges the encoder, decoder, all those terms, etc. But here, this one small difference. They don't do that. Rather, they use a sampling process to take one step more and get the data dimension. That's it.
Mm-hmm.
The idea being that this network would have learned enough information that even it can go from that some like slightly noisy version, that is X1, right?
Right.
Slightly noisy
Slightly noisy.
to the noiseless part, right?
Yes.
Apparently this works. So I mean that's the
Mm-hmm.
this is a part. Yeah. So again, so again, as we discussed, the bigger problem that we're trying to solve at hand is the sampling process, right? And what we have seen till now is how we can learn the parameters of the function, right? So how do we do the sampling, right? One thing is very clear. So we have to go to the backward process, right? The reverse process. And what does the reverse process do? It tells us, it gives us conditional values in this form, right? If I have a xt, I can go to xt minus 1, right? And what we also assume in the forward reverse process is p theta of capital xt, capital T, is a Gaussian distribution,
Mm-hmm.
right? That's how we assumed, and we formed all our KL divergence and formulation, etc. So now
Yes.
what, same process, we take xt from the Gaussian distribution, and then you take from t equal to, let's say, t to 2 or whatever, you will do this step. You will just go ahead, get the t minus 1th value from x, capital T, a small t. Right? So
Yes.
capital T you have, capital T to T minus 1, and all of that, all will keep on doing. And actually not
Mm-hmm.
just until you do it, until you have. Yeah. Then x1 becomes x0,
Mm-hmm.
right? But there's one catch. I mean, p theta of xt given xt minus 1 given xt is actually a random, what do you can say, is a distribution, right? At the end of the day.
Yes.
So and we already know how to, and it's a Gaussian distribution. So we know xt minus 1 is basically that mean whatever we learned, right?
Mm-hmm.
Xt comma t plus this variance term that we also had, right? That is sigma q of t times a random variable z, which is from Gaussian distribution. If you remember, why? Because we said p theta of xt minus 1 given xt is Gaussian distribution over xt minus 1 with this mean and variance of sigma q of t, right? Where sigma q of t was sigma q squared of t into I, right?
Mm-hmm.
So ideally what we do is we will look at xt minus 1 as this equation, that is mu theta of xt comma t plus sigma q of t z, okay? And
Mm-hmm.
now, what we had with us, the effect that we built was for epsilon theta, not mu theta. But we had the relation between mu theta and epsilon theta already, right? In the third formulation.
Mm-hmm.
So is then substituted here. That's it. That's the only thing that that we use. So where is that? This one, right? So this expression is then
Right.
used.
Mm-hmm.
That's the thing we will build. So now, yeah, so this is the mu theta part. So um, yeah, so mu theta of xt comma t is computed like this. This is something that we learned with the neural network just now, right? Use
Mm-hmm.
that to evaluate. You will get this mean mean plus this variance term is added to generate a distribution over xt minus 1. So that over time also, so unlike VAs and all, where you have like with the initial noise variable, you will have one particular value that gets associated with it, right? Here, because each of these sampling steps are also have some sort of variable in it, so it will not be straightforward to just map one number to a image, right? So each
Right.
one sample from the N0I will be associated with multiple different images based upon how the noise is, right? So where Z is basically taken as from this N0I. Now, one catch here is that see from x1 to x0. So from x1 to x0, again, what they do is they don't add this noise at all. Again, this is all very random for me also. But yeah, so t is greater than, so if t is equal to 1, right? T is equal to 1, then z is set to 0, else z is sampled from this Gaussian distribution. So this is the final sampling process. So after this t equal to 1, you will get x0, you just return x0. That's the idea. Is this clear?
Yes, yes.
So ideally, you should be able to implement diffusion models also. So you can try to beat the Dolly models that we have. Oh, sorry. Before that, you need to know conditional diffusion models, right? So conditional diffusion models. Again, same thought process. We use this idea even in conditional VAs also, right? So where we wanted to look at something like a set of images, but conditioned on some label. We have been working with this example of cat dog, right? Set of images, but conditioned on cat dog. So now what we do here is we look at this joint distribution of all these x0 to xt conditioned on y, such that this p of xt is still set to be Gaussian, right? So you start from the Gaussian distribution, but this p thetas, that is a conditional distribution of the reverse process, is now conditioned on this y, right? So each step, so basically see, from going from xt to xt minus 1 is the denoising step basically, right?
Yes.
So now this denoising step is now conditioned on this random variable. So if it's cat, it will denoise towards a cat image. If it is dog, it will denoise towards a dog image. That's the idea, right?
Yes.
Now, implementation for this, any thoughts you think very straightforward implementation that would be required? So because see, all of the theory will still hold. It's the same theory, it's the same everything, but there's one part is new, which is why, right? So how would you how would we incorporate that into the implementation that we have?
So just add the label also as input and learn the parameters with that label, and that's all.
Right, that's it. Right, so same idea. So basically now sigma theta or epsilon theta will now be a fact, will now depend on xt. There is a whatever the noisy version of t and time t and the label y.
Label y.
Because what we're saying I added some noise to the x0 with the label y. So this has to be equal to the noise added, which was added to get the xt. That's it, right? So your work now same thought process. Get x0, but you will take xt, you will take t. Additionally, you will also take y. That's it, right? Now, the issue in such approach is that again same issue like how we had with time embeddings. That is, it starts ignoring this y variable, right? So this conditioning variable that is there, that is sort of ignored by this network, right? So now then people thought, okay, how do we make sure it is not ignored? So this time embedding sort of approach worked with time because there is a clear-cut order among the time, right? So if t is equal to 1, is t is less than t equal to 2. But with labels, we don't have that, right? We cannot say dog then cat versus and all of that. So so then how do we go about doing that? So then they brought this idea of something called as classifier guidance. Again, this should be very sort of intuitive. The idea being that we have an additional sort of a network which is learned with this network that we have at place, which takes in xt and has to produce the corresponding y.
Okay. Okay.
Right. So this y is the same y here, which is used to as a target for this y. Right. So then what will happen? So basically then xt's have to be learnt in such a way that they have information about y.
Oh, I see.
Correct?
Okay. Okay. Makes sense.
So then what happens is all those gradients which are learnt here, which are again, see, this is all common. These are all common across all xt's, right? So all those grades which get updated, they have to predict the noise as well as predict the noise such a way that they also have information about the label.
Right.
That's the idea. Right? Okay. But can you see some issue with this? There's one small issue with this. The idea is great, but there's some small issue. Especially think about this condition.
It doesn't have a time input in this network.
Okay. Go ahead.
For classifier guidance, okay, fine. That is one, because like all classification could be dependent on time.
Why? Why should it be dependent on time?
Because the nature of the data itself is changing from every time point.
Exactly. Right. So let's say capital XT we know is a Gaussian distribution.
Yes.
Right. Nothing about the data is there here. But
yeah.
What are we asking the classifier to do? We're asking it to say xt minus 1. You have to keep information about xt minus y in xt minus 1 also. Right. It's basically the most noisiest image.
Right.
Most noisiest version in some sense, right? So basically all possible correlations that were existing in the image which could help it to predict y is almost lost
now. Yeah.
Almost lost. So we are sort of keeping a very strong sort of constraint on this classifier So one way to solve it is basically we can say, okay, the loss function you can weight with time.
Right.
We say, okay, for
that
x
like more for earlier time points and less for later time points.
Right. So we can say for x naught and up to, let's say, x t by 2, for example, right? You'll have a higher weightage on the loss compared to after this. Right, because after this almost any sort of information about the class might be lost because we have added almost to amount of noise. Right, that's one way to go about it. The other way is something called as classifier free guidance. To explain this, we'll need to look at something called as EBMs, which we will do now.
Okay.
Yeah, so it's 7:30. Okay, so I'll give you intuition about. There's something else pending. Fine. So we'll come back to EBMs in some time. Now, I just want to draw some parallels between VAE and diffusion models. So VAs, we had this latent sort of thought process, right? So we had X, we were going to a latent space Z and trying to reconstruct the X.
Right.
So is there something like that happening in diffusion models? Like what is playing the role of latents in that sense here?
So N0 itself is a latent. Yeah.
N0 is latent because see, what is the whole point of latent? They have to store, they have to be able to have information about this.
Correct.
Right.
Correct.
So here, if you look at it at a more upper level, the idea is all of these x1 to x, let's say t minus 1 for that matter.
Right.
All of these are playing the role of latents. Right, and this is the data that we have. Right. So what we're doing is we're going from this data to latent space. But again, here the point is we're going through time. Rather, here it was some sort of a transformation which you are learning or whatever, right? And we're going from these latents back to the data, right? So this basically, I mean, this sort of approach is there. So even without this diffusion model, this sort of approach is there in something called a hierarchical VA. So where you have multiple latents, you do this, you go
Okay,
up,
okay.
then again go back, and so on, right? This is something called as hierarchical VA. So this is some sort of a similar to this sort of approach, right? So
Hmm.
where the latent is being placed by is being played by all of these. Now,
Hmm.
previously we were using these latents as some sort of a representation of X, right?
Right.
Can we do that here though?
Sorry, could you please repeat?
So previously we were interested in these latents from a data dimensionality approach also, right?
Right.
Said okay, we'll make it less dimension and all of that, and now we can represent everything about X in that as Z space. But can I do that here though?
No, no, because all are like d-dimensional, same as the
All are
original data input.
exactly right. So now, so basically this data which is in RD space, we're actually I mean, in some sense representing it in this T into RD space. So R power
Yeah, yeah.
DT space, right?
Hmm.
Which is not at all a compression in any sense, right?
Hmm.
So that is the idea. So we cannot this latent. So though they play the role of latent in some sense, but it's not the traditional way that VA uses, right?
Hmm.
And VA has, I mean, this low dimensional thing came from the idea of manifold hypothesis,
Hmm.
right?
Right.
We said, okay, low dimensional manifold, so I want to discover that manifold, right? But rather here we are not doing that at all. Here, though your X data or your X naught will lie in more low dimensional manifold, as your time increases, that data will now start moving into a higher dimensional
Higher
manifold.
dimensional. Yeah.
Right, exactly. Because
Hmm.
now your X capital T has to be a Gaussian, isotropic Gaussian. So you need all the D dimensions to specify this XT. Whereas X
Right.
data could be in a low dimensional space. Again, we don't know,
Ah, correct, correct, correct.
right? Something less
Hmm.
than T. Here,
Hmm.
this has to be in RD space,
Hmm.
right? So that is the idea. So we're trying to actually change the over time. We are adding more and more uncorrelated noise. So you need more dimensions to be able to get the data, get the data back, and therefore that sort of manifold hypothesis is basically not, in some sense, being used at all in here, right?
Yes.
Okay. Now, what is the role of we had encoder decoder there, right? So here, what do you think the role of encoder and decoder are? So what could
So,
be a parallel in that sense? Go ahead.
so decoder we still have because like we are going from, for example, xt to xt minus one.
Right. Using the
Yeah.
P theta network that we built,
Yeah. Yeah.
right? So encoder.
We don't have actually an encoder.
So we have an encoder in the sense that it is fixed. There's nothing to be learned
Right.
about it.
Correct.
Because all of this process that we have x1 to, let's say, this x capital T, this is a fixed process,
Right. But there
right?
also alpha needs to be learned, no?
No. Again, see, alpha we kept it. We said alpha is something that we fix. We fix the schedule also.
Oh, I see. I see. Okay.
Yeah. So in the implementation, I mentioned that we beforehand only we say okay, it will follow some sort of something called as a cosine schedule,
Right.
right? So
I
that
see. Okay.
hence there's nothing to be learned. So this is
Hmm.
the difference versus in VAE we are actually learning the
Encoder also.
learnable
Hmm.
process, right? But
Hmm.
this is same,
Hmm.
right? Yeah. Okay. So hence it's a VA's far cousin. One variant, actually I'll mention this probably in the next class, but as you said, right, people did try this learning this alpha t's by the way.
Okay.
So
Okay.
it was a learnable schedule actually.
Hmm.
And it turns out there is a very nice interpretation also. So people have tried in interpretation in terms of SNR basically,
Okay.
signal to noise. So what turns out to be is that they so between two steps, let's say t-1 to xt, right? If you think about it, we are going from sorry, the or opposite, not the yeah. So we're going from a noisy version to a noiseless version, a less noisy version.
Hmm.
So in some sense, the SNR is increasing.
Yes.
Right? So this the amount of SNR increase, that is basically seen as some difference between these alpha T's.
Yeah, yeah.
And
Correct.
it is learned, then it is learned in some way. That's one version that exists, learnable schedule. Right? So yeah, LDM will do it next class. Okay. Last one thing I want to leave you with. So um, okay, let's come back to this very basic question. Um, okay, by the way,
So,
any doubts till now? Anything in doubts?
no doubts.
Ah.
So is it possible to like end by 7:45-ish because I have to like go somewhere?
Exactly same
Or
constraint. I'll finish it.
okay,
But
okay, fine, fine. Yeah,
yeah.
yeah.
Okay. So I'll give you one thought process. Okay. So let's say I have a random variable. Again, let's start with the same thought process. X is a random variable.
So
Let's say
this is
the
motivation for EBMs.
EBMs. Yes,
Okay.
EBMs. Yeah.
How do
And we'll come
you?
EBM.
Okay,
Sorry.
fine.
Yeah. Hmm.
What's the full
So
form?
I'm sorry.
What's the full form of that?
They're called energy-based models.
Okay, okay. I see.
Energy-based models. Yeah. Okay. So we have a random variable x, which is the data random variable, and we have a PDF on x, right? Let's again assuming observed continuous, all of those nice things, and I have a PDF, right? Px of x. Now, is Px of x a function?
It's a distribution.
But
Px of x is a function, yeah.
function, right? Okay. Uh, it's a function from what to what?
From x to Px of x.
Right? RD space 2. What values can Px take?
0 to 1, so like unidimensional.
We're talking about density functions.
Oh, density functions. What values? So again, like d-dimensional within the range of 0 to 1.
Probability density. Probability density will it be bounded? Okay.
No, it won't. It won't. Sorry. Yeah, yeah. Okay.
So
It's probably density function.
always remember this example. Uniform 0.5, right? This will have a density
Amplitude
function
would
of,
be 2. Yeah, yeah.
right.
Correct. Yeah.
Yes. Okay. So this number is okay. Can it be negative?
No, it can't be negative.
It can't be negative, right? So this basically goes from RD to R plus. Is this fine?
This is fine.
Zero also is sometimes allowed, but okay, we'll discuss in a while this small complication. Okay, so it's a function, right? So what do we do with functions in this course?
We'll learn the functions.
We'll approximate them, right? Using
Yes.
what? Neural networks.
Neural networks.
So why can't I just apply a neural network?
If you can
So I'll have
apply,
a neural network, let's say I'll call this. Sorry.
you can apply.
So I'll have a neural network p theta. Sorry, I'll have a network theta. Let's say some parameters theta. And what it will do is it will take in RD image or RD sample and give me out a value which is generally positive or non-negative, right? I can do that from using some appropriate activation function,
Yes.
right?
Correct. Yeah.
Right. Now, do you see any issue in this? Okay, I'll do one more thing. Let's do one thing. So, okay, because I have to give, non-negative real numbers. Now, I'll let's assume that 0 is not allowed for now. Okay.
Okay, fine. Yeah.
Go to any low value, but 0 is not allowed. Let's say. Okay. So what we do? I will have this function. Let's say f theta. Sorry, f theta of x, right? Which takes in a image, and I will raise it to e power minus f theta of x. Right. So this is always positive. And the minus f theta of x is sort of giving me some sort of a negative logarithm of the density. Okay. So it's always positive. That's fine. Is this enough? Can I write px of x like this? Is there some property that px needs to satisfy to be it a valid density?
Right. So the area under the curve should be like equal to 1.
Right. That has to be equal to 1. So if I have a learnable function also, the issue comes in this setting, that is e power minus f theta of x
won't
dx
be equal to 1.
Has to be equal to 1. Now, this enforcing this for a neural network is the question.
Right.
Okay, this is one issue that we have. Let's put a pin in it. And I'll leave you with one last thing. So let's say I have two functions f and g such that f dash of x. Okay, let me just put this is point number 1, point number 2. Let's say f dash of x equals to g dash of x, two functions for all x.
Okay.
Can I say anything about f of x and g of x? Is there any relation between them?
They might be equal with some like added constant.
Right, Hannah. Correct, because so plus c, right? Because
Plus
how
C,
will
yeah.
I step this step from this step to step from using indefinite integrals, right? G dash of x. When I solve for this, I will get f of x is equal to g of x, right? Because this integration constants. Now, let's say f of x and g of x are probability density functions, PDFs.
Okay.
Okay. What will C be?
Zero.
Correct. Why?
Because the integral of both of them should be equal to 1. So there is no scope of adding any constant then.
Right. So then if I integrate both sides, C will be equal to 0. Now, this gives me one sort of a idea where, let's say I have px of x, I have p theta of x. Right? Now, if I look at the derivative of p of, if I try to match the derivative of these two functions, then by default, I'm actually learning the true distribution. Is that correct?
True distributions. Yes, that is true.
Previously, we were taking this approach of KL divergence. We said, okay, KL of px, p theta, minimize this and all of that. Here, the approach is completely different. We're saying, look at the derivatives of the two functions.
Correct.
Now, one last thing. This derivative is with respect to what, by the way?
With respect to x.
X, right? So this is del x of px of x. This is also del x of p theta of x, not
p theta of
del p, not del theta.
Yes.
Right. So I still need to get the gradients with respect to theta so that I can learn them.
Yes.
Right. At the end of the day. Okay, so we'll stop here and we'll see how EBMs try to approach this problem.
Okay.
ठीक है?
Yeah. Thank you.
Yeah. Okay, man. Chalo. See you.